Well, that's true. Okay. So you can hear me, I think. So we're going to keep doing same thing as last time. We're definitely at the point where the good news is more of the situation is that I owe all of you and you don't owe me anything. Like I owe you points that I see they're coming in, all the things I see that you guys are submitting the stuff that you said into the portals for points, which is exactly what you should do. And I'm totally psyched that people are taking this seriously. It's clearly having an effect on class. We're going to keep doing it, but I also want to make clear, you might have just seen, and we're going to shift the topics now. We're going to move on in the material, which is sort of great. But you may have seen that I updated those assignment portals. I mean, because you are taking them seriously and we're taking them seriously, meaning that not only are the same rules today going to apply, like if you say anything at all in the public chat or in public voice, then you submit it for the 50 points of homework. And it's like instead of homework. And if you say anything that's verifiably yes or no, like right or wrong, then you submit that and you can double dip and all that. But also, like if you weren't here last week or you didn't say something last week or last time or whatever, then you'll notice like I put those assignment portals are still live and you can still use them. So you could say like a bunch of things today and retro put things in old. Okay. So like it's all, any one of you who really is just struggling with, just really wants to be quiet, but is totally paying attention, talk to me privately, like, and we'll figure something out. But I am saying it's not a deal of if you miss a class, then that's it. And you just missed your opportunity for the points forever. No, like you can cross apply them to different days. Okay. Just to make that clear. All right. So we're going to start with a problem that, oh, sorry, question.
Sorry. I just wanted to ask a quick question.
Oh,
so for the two parts where we have to first just submit anything we talk about, do we have to do both sections? Like say we say something but it's not like verifiable as right or wrong, do we have, like, is it mandatory to post something on both of them?
Oh, wait, that's a great question. No, that's a great, totally fair question. And first of all, no, I didn't mean it as mandatory at all. No, it's not. That's a good point. Like you don't have to do the other thing. It's meant to be like extra motivation or extra bonus. But now that you're mentioning it, if I'll also take that question a step further, like in other words, what if someone says two things, like exactly what you're doing right now, it certainly counts as something. And if you did, but even if I didn't say like it's right or it's wrong, and if you did this twice, could you? Yeah, I see the real question behind the question, and it's totally also a good way. And I'm trying to say something clear about. So, yes, I think it should be the case. What I want, yes. I mean, the more people talk, the more they should be rewarded. So like, even if someone said something twice in a day or once today and once yesterday, that neither of which was like that other extra thing, they still should be totally rewarded each time. Absolutely. And no, it's not mandatory to do the other thing. I will try to improve this point structure though. So I do, if really what you're saying is like, there should be a way that you can keep getting rewarded, even if you keep saying things, even if they are not always like the right or wrong thing. So I will take that seriously and figure out a way to like.
Because I like added the document with all of the things I like contributed to the class last week, and then for the second part, I put, because I answered the first question last class.
Oh, right.
So I put that as the right or wrong.
Oh yeah.
I'm sure that's exactly like what you want.
Oh, no, yes. No, you did fine. No, that is right. I'm sorry. No, so this is even simpler than absolutely you did the right thing. And if there's any doubt in your mind, yeah, if you're not sure with whether something like totally categorizes or not, definitely take the risk and put it in. And like in worst, I'll say, no, I don't think that counts or whatever. And I'll tell you, but no, you did the right thing. And you definitely did the right thing. Yes. Wait. And so I just realized, but yes, well, you did the right thing. You're fine. You're totally fine, right? And
I just want to clarify.
I'm sorry. Oh, no problem. Right, and to everybody, like the more we do this, and the more I could see more and more levels at which I should add like more layers of points, and I'm happy to do it. I just don't want to make things so complicated that the cart breaks the horse or whatever. But yeah, like anyway. But yes, it's already happening. I think that everybody. it is one of these things where the points hopefully multiply themselves, like and don't get in the way of the class. Like I think everybody's just talking more, and therefore everybody's grade's going to get better, no matter what. But anyway, yes, I think that was a fair question. So I'm going to now ask a new physics question today to everybody that comes from lab 3 and lab 4, like is where we were. I was sort of trying to get to lab 3 and lab 4 in the material in the class last time, but now I'm going to be a little bit more direct about it. So just to be clear, what we're really now starting to talk about as of today, we're explicitly going to start talking about two-dimensional problems, three-dimensional in principle, 4, 5, any number of dimensions. Like really, we generally stick to 2 and 3 because that's what space seems to be. But we're now going to enter the land of physics where we take the techniques of, or the understandings we have of motion in one line, and then we learn a technique for how to deal with more than one line at once. And that technique is called vectors. And from that technique, we then decide, we can deal with as many axes of space as we ever need or as we ever want. We can deal with 1 dimension or 2 dimensions or 3 or 4 or 5 because we have a technique for dealing with more than 1 dimension at a time. That technique is called vectors. So this original problem, this first problem that I'm giving you is kind of like from lab 3. The givens are, and like same as last time, I'm going to turn the page in a second, so obviously you want to have these down, but just imagine that I walk 5 meters due north, and then I walk 8 meters northeast. So I'm assuming this I'm assuming this kind of world. Okay, so I haven't even asked the question yet, just to be clear, like I'm giving you the setup of our new question. And this is now our official foray into two-dimensional kinematics, or like we've been doing one-dimensional kinematics, one-dimensional motion is what we've been doing. Now we're getting into two-dimensional, or you could call it n-dimensional kinematics. Okay, so I'm starting with this situation like lab 3 where we're talking about displacement. So like this is all about today is about displacement vectors. So you're imagining I walk, sorry, so I just entered. All right, so I walk 5 meters due north. So in this coordinate system from here on, in my coordinate system, which is now encompassing a plane, 2 dimensions, north I'm making up on the page, as is traditional. South I'm making down. East I'm making right. West I'm making left. Like you can do whatever you want as long as they're oriented relative to one another properly. But notice I'm choosing a positive and negative like I always do, but I'm choosing a positive and negative for each axis. So we're now in a world where positive and negative is how we distinguish direction, but we do so one axis at a time, because everything we've learned about physics, whether it's as students or as physicists, like everything we've put together as physics so far is how things work in an axis. So on each axis separately, we have positive and negative designations, kind of important. Then to capture a direction in two-dimensional space, now to capture direction, it's not sufficient anymore just to say positive or negative, because you don't know if that means, if someone says negative, you don't know if that means south, or does it mean west, or does it mean somewhat in between south and west, like southwest. So how we now talk about directions is with angles, acute angle. If we're physicists, we use acute angles that are measured kind of like in math, like from the unit circle there. And this, again, this is like super boring, but super important to just that we all be on the same page with these like agreements. We're all going to agree that if we picture axes like the ones I've just drawn here, we're going to always open up our angle from the positive x-axis, just like in math, just like in the unit circle. We're calling that positive x-axis now like the east axis, the due east axis. We would call the negative x-axis like the due west axis, so to speak, right? We open up angles from due east. We open them up like not to counterclockwise, right? Again, just like math. And any angle that we talk about, so, like means measured in this coordinate system. So just to be super clear, again, I haven't even asked the question. I'm just trying to set up the givens. But if the given of this problem is that first I walk 5 meters due north, and I then walk 8 meters at 30 degrees northeast, like from now on, what that means, and you've heard it your whole life, but I just want to be, precise in a physics sense. If someone says northeast, well, yeah, they mean between north and east. But more specifically, if they say northeast, like notice down here, when someone says northeast, I want us to realize what they really mean is north of east. They mean an angle that got opened up from the east and is measuring how big it is north of it. So if someone literally just says northeast, they're assuming, just like if someone just says east, like if they mean anything precise, they mean due east, exactly east. If they just say northeast, they mean exactly northeast, like as much north as it is east. So they mean like 45 degrees north of east. But if you want to be more precise, if you ever have traveled like through the woods with a compass or on an airplane or something, like if you've ever looked at a compass basically, which is tricky at first, I might add, but if you've ever used navigational directions, then you can be more precise and you can say something like, I'm bearing 30 degrees northeast, as we are saying this problem. And I want to be clear that what you really mean by what we mean when we say 30 degrees northeast is we mean 30 degrees north of east. We mean picture an angle being opened up from the east, and picture the second line of that angle, the reference line or whatever, going 30 degrees above it. That's what we're saying, as opposed to, and here's where, just to make sure we're all, as opposed to if someone said 30 degrees east north, which is a thing. It's like a super awkward thing to say, and you would be surprised if someone, but it is different. 30 degrees east north would be opening up from the northern axis, opening up to the east. In other words, 30 degrees, just to be super clear that the language, if you say 30 degrees northeast, what you mean is exactly the same thing as if someone said 60 degrees east north. In other words, the words are not a throwaway. The order you say them. So if someone says southwest, they mean south of west. And that's how you know where to draw the angle. If someone says southwest, they mean this angle, not the other one. That's important because that can get very confusing if you're not clear on it. Okay, so I'm just going to start. So the problem that we have here is, and I can go back at any point, but what the situation at hand, the givens, are apparently that one, I walked, I think I said 5 meters due north. So I walked like that. Then I walked, I believe, and I'll check, I believe 8 meters, yeah, at 30 degrees northeast. So after I did that, I went like this. I went a longer vector, like I went a longer distance, 8 meters. And I did it at this angle, 30 degrees north of east, okay? So I wanted you to see, and I still haven't asked the question, although if you're following this, and if you're bored to tears or whatever, you probably could guess what my question is gonna be. Like the first question I'm gonna ask is, in a way, the most straightforward one to ask, assuming that what I've just drawn down is my two separate motions, but let's assume that I did them consecutively. Like assume that I began displacement number 2 from precisely where I ended displacement 1. If we assume, so assume this is really like normal walking. I walked 5 meters north and then stopped. I had a sandwich, whatever. And then from that exact location in space, I then did with this, I then walked 8 meters at 30 degrees north of east. Okay, so I did these two motions, but I did one from where the other left off. then my question, so assuming all that, so I did a displacement, then I did another displacement. What I want to know, of course, I sort of in the course, sorry, what I want to know so as usual, I think this question that I'm asking is like, once you look at the setup, if you understand the setup that I'm saying, I do think this is the obvious question to ask. Like, I do not think the answer is obvious. I am not saying that. But it's the obvious question to ask, meaning I think it's a fair question. Like, I could actually imagine doing this thing and then wanting to know how far did I actually get in the end and in what direction, right? And by the way, that is what I'm asking. I'm asking that, I'm turning it over to the class. And this will take, you cannot get it in your head. I cannot get this in my head, by the way. So it will take a beat or two. So let me make super clear what the question is. It's simple and fair, but it is not easy or obvious. The question is, what's my total displacement? Meaning, like if I started here and I ended there, like if I put this all together in one diagram that's sort of to scale, if I did, and you can, and that is a way of figuring out, but if I actually put this like to scale, I want to know that final arrow that connects the original tail to the last tip, if so to speak. I want to know how long that triangle is, like how far did I actually get overall? And I want to know exactly in what direction it's pointing, meaning what direction according to the compass. Not like, so I really want to know, this is what I want to know. And if you draw this well enough, you could get it from drawing, but it's not the only way to get it, and it may or may not be the best way. But I really want to know how long is that arrow, and I want to know what is this angle right here? And note, if I drew this well, right there, meaning I want to know, say I drew this well, say that arrow does point somewhat northeastish. I want to know what the northeast precise angle is. I don't want to know an east-north angle because nobody talks that way, right? And maybe my drawing is bad, so maybe the answer is like southwest or something. But whatever the final vector, whatever the final arrow points, I want to know how it's pointing compared to an imaginary reference horizontal axis, like just like I said at the beginning. So like that's so the answer I'm looking for here, I want total displacement, which really means I want an arrow that has a length or, a magnitude, a size, and has a direction, which in this case really means an angle. I want both as a final answer. I cannot get it in my head. It is that hard. I don't mean like that, but like you have to do something, and it could be drawings, or it could be a bunch of drawings, or it could be calculations, or it could be look back at lab 3 and lab 4. I'm going to get the answer 2 on paper, like while we're doing this, but this is, well, so that's the question is if I did these two, so what I'm really asking secretly is, can you add these two displacement vectors? These arrows are called vectors, these arrows that have size and point in a certain direction. What I'm asking in physics terms is, can you add these two vectors together and get a total displacement vector, a resultant displacement? What I'm asking in physical regular terms is, if you walk that way and then you walk the other way, how much did you walk overall and what direction? And I'm not asking you to memorize any, there's no new formulas or anything. I'm asking you to reason it out, and I'll give hints as we go. But the biggest hint of all is, remember from last week, this is a two-dimensional problem, but what it really secretly is two one-dimensional problems occurring simultaneously yet independently. Like that thing that we tried to end on last week is, but there's no new, you don't have to know some math equation that I haven't taught you yet or anything like that. But this is what I want. So I'm going to shut up. I'm going to just solve it privately on my piece of paper. You can ask questions. You can do whatever. People will get points up the wazoo, but this is the question. Oh, and if you use calculator at all, which you might well at some point, have it in degree mode, not in radian mode. Doesn't mean you have to use a calculator, but if you do, have it in degree mode, not radian mode. Oh.
Okay, so I didn't get the answer, but I just wanted to share a mistake I made. So I drew out the triangle basically that would give us like the 5 going north and then the 8 going northeast, and then I drew a line connecting the point where we ended and the point where we started, which would be the displacement. But I did use Pythagorean's theorem to try to find the displacement, which is wrong because it's not a right triangle. So I just wanted to share that part of my process so that you guys might not make the same mistakes.
That is totally awesome. All right, that totally, all of that totally counts, please, as like a triple, double dip, if not a triple dip. Yes, I totally appreciate it, and I'm glad that she. Anyway, yes, that is super. I want to actually draw something of what she just said. That is really super helpful. There's a lot of what she said that actually is major league right and mileage, so much so that she might not even know it, like mileage toward the answer, and then one like left turn or something at the end that is a pitfall for some people. Like if you get far enough, one might make the mistake that she's talking about. But you, first of all, you already have to get far enough to even make that mistake. So this is super helpful, like to introduce the idea of Pythagorean theorem and right triangle properties. We totally need them. We can't solve this problem without them. It's just right. It's true that somewhere in there she treated a triangle as though it was a right triangle, whereas it wasn't. But yes, let's get this totally a major insight. We have to use right angle. Like we have to know our Pythagorean theorem. We're going to use it. We even do have to know SOHCAHTOA and use it. Just maybe not exactly where we might think. Come on, I just lost the board. I just lost the, now I'm twice. Wait a minute. Okay, sorry. Okay. Okay, she is saying, that's great. No, I totally, and I think it did take a lot of guts to say a lot of that kind of thing. Totally helpful. Wait, let me just now draw. So we have, first we did, and then, sorry. Okay, first we did this. This is called a vector. This is an arrow that represents a vector quantity, right? Like the vector quantity is the displacement 5 meters with a direction due north. It's a vector because like it has magnitude and direction. Here is an arrow, golly, here's an arrow that I'm drawing to represent that quantity. This arrow is called a vector. And notice, it really is a great representation because it captures exactly the two things. The size, like if I want to draw a 10-meter displacement, I'm going to draw an arrow hopefully twice as big. And it also captures direction, like in a plane, because it has a tip versus a tail. Okay, so we do this. And now, here's the thing sorry, I should really draw it lower on the page. I'm sorry. We went 5 meters. Like I'm trying to draw right now everything that Sarah just said that's so right and helpful. And a lot of you may have done it. And we should do it, what she's saying. Like first, I went 5 meters to the due north. Then, from where I landed or ended temporarily, I then started my next displacement. So it makes total sense to put these two arrows together, as Sarah did, I believe, to put them together specifically in a tip to tail fashion. Like I'm going to start the tail of the second vector at the tip of the first vector, right? And I'm going to like follow the directions of it. I'm going to make it longer, which makes it 8. I mean, I make it, and the better I am as an artist, or the more I'm paying attention to the graph paper, the more I'd want to really make this to scale. Right now, I'm kind of sketching it, but the more it is to scale, the more my drawing will really show the answer. Okay, so I draw that 8 meters and I say, okay, that is supposed to be, is supposed to be at 30 degrees northeast. Now notice this is why I had to yammer so much before about this technicality. Notice how I am drawing these two vectors tip to tail, and that is what you do. That is not just a random good like intuition on Sarah's part, but it's actually the formal technique for adding two vector quantities. You do place the two vector arrows tip to tail. In fact, I'm going to write that right now. Like this is a correct thing to do, to add vector quantities of any kind, like right now we're talking about displacement, but if we get this right here, where we can picture people walking, then it's going to apply to velocities, accelerations, forces, fields, quantities. We place vector arrows tip to tail. Like it just sound, that is actually a technical thing. Like we place the arrows tip to tail, and we believe that by drawing them properly and by placing them tip to tail, here's the insight of what Sarah's saying. And it is an insight. Like she might just think this part is like the obvious thing to her, like it wasn't even worth mentioning or something, or maybe some of you might think that, but no, if it seems obvious to you, then it probably is really true and really important and is the insight. What she's sort of assuming in her treatment, what she's assuming correctly, is that if we could get the size and direction or the orientation of that last arrow,
After seeing your work, I realized that, because before I thought the angle was 45 degrees, but this made it a lot more clear that I think it's 120.
oh, wow, now you're way ahead of me. No, this is great. And thank you for saying that this is making it clear, but I'm really honestly also telling you that it's you that said the thing that's making me able to do this. But thank you. But yeah, okay. And I want to get to that 120. That's cool. A couple of things that still, yeah. So first of all, I'm saying like, it seems obvious maybe to some people once you draw it. We are actually saying though that these drawings are a calculational tool. Like remember, digital calculator, or electronic calculators, not to be weird, I don't want to be like grandpa about this, but you know, electronic calculators are still only a couple of generations old. And this math and this physics has been, well, the physics has been done for hundreds of years. The math has been done for thousands of years. People have known this stuff for thousands of years before calculators. So how the heck did they do anything? Their calculation tool was drawing, like for real. The people that could really draw and draw to scale and stuff, figure out things with the drawings that are totally reliable. And so here, one thing is, we're going to really draw these, we're going to use, if we draw vectors correctly, follow a couple of rules, our drawings will reveal not only good sense of the answer, but the answer itself. In other words, Sarah's right to believe that, or what I'm trying to write here is the size of this arrow, if I draw everything to scale, and the orientation of this arrow, like where the tip is and where the tail, will literally show me the magnitude and direction of the final answer that I'm looking for. Like if I drew this well enough and I measured that, and this is the point of lab 3 in a way, if I drew this well enough and measured that arrow with a ruler and then measured that angle with a protractor, it should literally actually be the right answer. Now I'm not even using it that way. I'm just using it to give me a sense of the answer. I'm still going to analytically figure it out through triangle stuff, but that's how much we trust these arrows. But now what I'm going to say is, notice one thing that I think Sarah is saying to everybody is, notice my 30 degrees. This is the part, honestly, this is a part that everybody does mess up generally for a while. Notice how carefully I've made that the 30 degrees is between the green arrow. I'm not changing it. I'm just trying to make it clear. That 30 degrees is the angle between the 8-meter long arrow and an imaginary horizontal green dotted reference line. Like it is not what everybody would think. And I don't even know if Sarah thought this or not, but I mean, what everybody would naturally think if you put these arrows together is that the 30-degree information, yeah, the calculator should totally be in degree mode. As long as I gave these angles in degrees, the calculator should be in degree mode, yes. Blah, 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 blah. What would I just say? Yeah, that 30 degrees is not between the two arrows. The easiest mistake to make, and honestly, it's such an easy mistake to make that you might not even know you're making it if you just copy, like, this is why it's important that everybody make their own diagrams first before they copy mine. If you just copy mine, it won't even occur to you that someone could make this mistake. But the 30 degrees I'm saying is just literally the direction of that second arrow. Like the 30 degrees is north of east. It's part of that second arrow's information, no matter whether there's any other arrows in the problem or not. Like the 30 degrees is not between the two arrows. That's the key thing I'm trying to say to everybody. The 30 degrees is not an angle between the two arrows. It's not a relationship of one displacement to another. every displacement has its own angle. And like technically the first arrow here has an angle of 90 degrees. Like it's 90 degrees north of east, it's due north, right? Anyway, so that's the picture here. So then, yeah, we've got a triangle here, and we do have two sides of it. Like, again, where Sarah's totally, like one side is 5 and the other side is 8. We can do whatever math we know to figure out that third side, and we are trying to figure out that third side, but it's true, we cannot treat this whole triangle as one big right triangle. That's true. That's an insight that I'm going to use Pythagorean theorem somehow, somewhere. I'm just making this clear. I am going to, and I'm even going to use SOHCAHTOA. But I can't do Pythagorean theorem to literally this big triangle here, because there is no, and that will, but there are right triangles to be found in this picture or in this situation, and there always will be, no matter how random the directions are. I'm looking in the chat. Let me see. Oh, sorry. Okay, no, I think I've answered it. So I guess my hint is this is all correct so far, but there's smaller triangles to be found. I guess is my hint. Somewhere there are right triangles to be found to be used to get the answer. I might give another hint, but well, yeah, I will give another hint. We do want to use right triangles, and we don't just see them staring us in the face. But the reason I can guarantee that there's always, well, I'll give you a hint. Well, yeah, there's always right triangles somewhere in the vector situation, because the north-south axis is always at right angles to the east-west axis. The right angle that's always there to help us is the right angle between our two independent axes. They are at right angles to each other. So somehow there's a right triangle that can be made between east and north or something like that. And once anybody sees that, that will be the next insight. But this is right so far. I'm just going to be quiet. I might even go to the restroom. Excuse me. I was just typing something in the chat, and I just saw something in the chat that I think is very correct, to say the least. So if I'm reading the chat, I'm saying this out loud because I don't want to disturb anybody. I was, as I say, I was just about to put a hit in the chat, and I still might if I don't lose it. But what Armand just said is super right. Super right. And I'm not even going to embarrass him any further by saying that this man knows how to show up early for a class, early enough to shame me into showing up even earlier next time. Okay, that is definitely right. So I think the hint I'm about to give, we'll just confirm. Oh, yes. Yeah, you can, yeah, and just, sure. Yes, absolutely. And then if I say it's right, like I might ask you and Armand to explain it. So, and I'm going to just put my hint in here too, just so everybody can see it if it helps. But I think now between Armand, whose name I'm not pronouncing, sorry, well, between Armand and Justin, probably the hint I'm about to give, I think they're past, but it may still be helpful to anybody else. And by the way, I'm saying to Justin, he should definitely post his answer. That doesn't mean, obviously I haven't seen it, so I don't know that it's right, but I'm saying, yeah. Oh, and thank you. That's awesome. Okay, thank you. This whole chat thing is crazy. I don't know, computers are crazy. I am a grandpa. Hold on. I'm not actually a grandpa. Hold on. But I'm gonna write my hint anyway, if it helps. Wait. Again, my hint might be redundant. I'm looking at it. Oh, sorry. Oh. Oh, okay. And hold on. So, and there are a couple, let me just say in two. Oh, wait, let me see. Oh, wow. You guys are saying, oh, I see. Okay. I'm now falling behind. Wow. Awesome. Awesome. All right. Let me say one thing. So there are a couple of things that are happening in the private chat also. And I think people are using the private chat correct. I really want to commend you all. I think for the most part, what you're deciding to put in public versus private, totally, for the most part, is the right decisions. And again, to remind everybody, I think using the private chat for things that it should be used makes total sense. It's just I can't give points for the private chat. Like it's for matters that are not about points, right? But there are a couple of things in the private chat now. So give me a moment to respond to them. But let me also say, yes, that answer is correct. Very correct and very impressive. And it sounds like they both, yeah. And so clearly tons of points to all, and God bless. If those guys, either of those two guys or anybody wants to start explaining, like those answers are correct. So if you, that's great. And anybody who's telling me in the private chat stuff about that, awesome too. And I believe you. If you guys want to start explaining or talking, that's great. I'm just going to respond to a couple other things in the private chat. Give me a minute. But yes, that's awesome. Hold on a second. Excuse me for 1 second. Okay. What is it? I'm looking. Okay, so now I'm looking at the chat again. It's very conceivable. So I'm going to go start talking this through in a second if nobody else wants to, but I'm totally psyched. And I think people are moving. This is great because I think this is not an easy problem. I think you guys did move somewhat fast toward a right answer, but just slow enough. I think you actually know what you're doing. And I mean, anybody who did that. And I think it is going to be worth explaining now. I think it's going to be easier for me to explain now that I see where people are. One thing before I explain it or move forward. Yeah, it's totally conceivable that some of you may like the proper answer here, since we're now in two-dimensional land. So any proper answer to any vector question, like what is a displacement, will always have two parts, like two parts, magnitude and direction. And that was always true for us in physics. Like if you gave an acceleration, you had to actually say if it was positive or negative. But that isn't so upsetting to people so much. Now we are saying from now on, when you give two pieces to an answer, you have to give a size and a direction, which now is going to be a very specific kind of angle. That is a bigger burden on all of us. Like physics does get harder in that sense that we always have to worry about angles now. And that means we have to know how angles work and stuff. I'm saying all that to say, though, it's extremely conceivable. So right, technically you're not right unless you have both parts. Like if this were an exam, you would get separate points for each part, the magnitude and the direction. It's very possible for many of you in the room to have the same correct answer for the magnitude as, if I may say, Justin and Armand, and you might have a different angle. And what that literally would mean, that wouldn't surprise me. It could happen to a lot of people the first time. It would mean you totally want to pay attention to whatever I'm going to do. It would mean it's not a coincidence that you got the same distance as them. Like it means you did a certain part very, very right. But then if you do have a different angle, if anybody's having the honesty to admit that in the chat or whatever, if someone got the same distance as Justin Armand, but got a different angle or even an angle, but they think it's southeast or something like that, well then, yeah, that's not just a detail, it's true. That doesn't mean, oh, I just forgot to carry the two. It means probably something is wrong over there that we have to look at. But it's totally true that these are two separate parts that together make the thing. It is possible to be right about something and not the other. Okay, let me now, oh, great. Let me just look. So I'm gonna do this in 1 second. One second. Okay, I'm going to start. So it starts, the key thing, honestly, to doing this is to recognize that we need to deal with right angle. Well, the key thing to recognize that, I won't make you write it again right now, but the key thing to recognize is that we got two one-dimensional worlds here happening independently but simultaneously. So the key thing to do mathematically is to try to break this problem up into two independent one-dimensional worlds. The way I do that, and this is called adding vectors by component method. So the thing that, and the major insight of this is when one of those two, when someone put in the chat like, oh, we can use the 30 degrees to get a north and an east component, like however they put it, that was the key. Yes, that's how I knew they were doing. We are now adding vectors by components. And the reason I'm trying to stop and say in English like what we're doing is because it's somewhat easy to picture and invent on our, not easy, it's possible to see and invent and picture this method on our own when we're talking about displacement vectors, when we're picturing people walking, when we're picturing arrows representing actual distances in larger space. But just remember, everything we say here, which will hopefully make sense to us with displacements, is going to carry over and be true to all and any vectors for the rest of our lives in physics, however far we go. Velocity, acceleration, force, field, etc. And in areas where you would never, no one would be picture that this would work or would know what to do unless they already had this tool in their bag. So this is a general tool, adding vectors by components, and it works for any kind of vectors at all. And the way the tool works is you first separate the world into two worlds, an X world and a Y world, okay? And what we say to ourselves is, oh, okay, the problem here is we're being asked to add two-dimensional displacements together. We're being asked to add, one two-dimensional trip to another two-dimensional trip. We don't know how to do that, but we know how to add one-dimensional things to each other. We know how to add numbers on a number line. So what we're gonna try to do is we're gonna zoom in on each there's no way you can read this, but we know we trust our ability to navigate the x-axis by itself, and we trust our ability to navigate the y-axis by itself. So what we're going to do is take each one of these motions, each vector by itself, in this case, each displacement vector, but whatever kind of vector it is, we're going to take each one and separately resolve it into what its impact was on the x world and the y world separately. In other words, so I'm going to turn to the next page and then back. So we're going to make a chart where we're going to fill in entries into the chart by, in fact, we're going to take, so this method is going to work for as many vectors as we might ever have to add up. Like this will work even if we had taken a 3-step journey or a 4-step journey, but each one of our parts of the journey, each vector, each arrow, we're going to ask ourselves, how far did it bring us X? How far did it bring us Y? And we're going to enter those values into this chart and just tally them up separately. So in order to get those values, so we're going to have 4 values to go into this chart. The X and Y piece of vector 1 and the X and Y piece, or impact or consequence or effect of vector 2. And how do I get them? I zoom in on each one. So here's vector number 1. I zoom in. Now vector number 1 was very straightforward. It was just 5 meters due east. I'm zooming in, I mean due north, sorry. I'm zooming in on, I'm looking at it. I don't really have to look any harder than I already did to realize what's this vector do for me? Well, it brings me positive 5 meters to the north, and it brings me 0 meters to the east or west. Like just looking at it, I can tell technically this is a triangle, if you like. This straightforward line, I mean, the straightforward arrow pointing up, if you like, you could think of it as a triangle with one leg being 5 and the other leg, you could think of it as a right triangle where one leg is 5 and the other leg is 0. Like it's a limiting case. It's a triangle brought to the limit or brought to the asymptote or whatever. The other side is 0. And the hypotenuse, therefore, is 5 squared plus 0 squared, 5 squared. Now, you don't have to think of it that way. That may be a crazy, dumb way to think of it. But I think it's clear that this first vector brings us 5 meters north and it brings us nowhere east or west. Whereas the second vector is actually more complicated. Therefore, it's almost easier to work with if you know what kind of work we're trying to do. The second vector, and this is what the insight that was in the chat, right? The second vector, independently existing like this, right? Like it was north of the east axis. It wasn't, I mean, it was 30 degrees north of the east axis. It wasn't like 30 degrees related to the other vector. It doesn't need the other vector to know what it's doing. Oh, and in fact, I didn't really draw it very nicely to scale, did I? Oh, sorry. Okay, like now it's more to scale. That's like longer than the other one. Well, what did this vector do? Well, if you think about lab 3, the whole purpose of lab 3 was to get us to realize that if you, but all you have to do is ever go to college in Manhattan, and you know, if you want to go 8 meters to the northeast, that's equivalent to, and sometimes less convenient to, and sometimes more convenient to, going some amount to the east and then some amount to the north, right? In other words, northeast equals north some amount plus east some amount. Only I'm going to write it as east plus north. I'm saying if you go northeast, what you did was really like I want to add the vector 8 to the vector 5. But I have to be careful about how to add them. But what I'm in a way doing is I'm thinking like in real life, it's like saying before adding the number 8 to the number 5, it's like stopping and recognizing, well, 8 itself is like 5 plus 3 or something. Like this vector 8 at 30 degrees to the northeast itself is composed of, it is the sum of 2 smaller vectors tip to tail that I can draw tip to tail. And in other words, before I add this 8 to anything, I'm going to think of the 2 pieces that add it up to make it. Why would I do that? Or why does that not send me down a rabbit hole? Because I'm thinking of 2 vectors that together make it, each of which functions completely independently on a coordinate axis. Like to go 8 meters, it's like being in Manhattan where you're only really allowed off, you can't walk through buildings, so you often have to go on the grid. And 8 meters off grid this way is really equivalent to, well, I know SOHCAHTOA, right? I know that sine of 30 is going to equal the opposite over the hypotenuse. I know cosine of 30 is going to equal the adjacent over the hypotenuse. Now, in this case, the adjacent is like the x leg, right? And the opposite is the y leg. So y really equals hypotenuse times sine of the angle, and x in this case equals hypotenuse times cosine of the angle. And what is the hypotenuse? The hypotenuse is 8. So in other words, I'm using SOHCAHTOA, which I have to, and I will every time I'm using SOHCAHTOA. You might say I'm using it backwards, like I'm knowing in my mind that sine equals opposite over hypotenuse. Therefore, for the rest of time in my mind, as a physicist, I go backwards, and I always think opposite equals hypotenuse times sine. That's, I think opposite and sine, and adjacent cosine. So I literally put in here, this is 8 cosine 30, that leg. This is 8 sine 30. I'm going to just draw this, right? All I'm doing is I'm taking one, I haven't added anything. I'm taking one of the vectors and making one of the vectors itself into its own right triangle. And in fact, that's what I'm always going to do. Any vector at all that isn't obvious, that isn't just straight along an axis, any vector that's tilted at all, I'm going to treat it as the hypotenuse of its own right triangle, because it is. Because any vector that brings us in two directions at once, like north and east, is really bringing us in one direction at the same time as it's, but independently of the fact that it's bringing us the other direction. So before, I'm going to look at the chat in 1 second, but I'm still just zooming in on this 8 to really understand what the 8 means in space. The 8 really means that it means the sum of two components, which notice I'm adding tip to tail. So I'm saying in vector language, 8 cosine 30, and I know there's something in the chat, I will totally get in a second, I'm sorry. Or maybe it's, well, either way, whether it's public or private, I'll get in 1 second. I'm saying this, and note it, and now, and I know, again, SOHCAHTOA, this is totally SOHCAHTOA, and there was a moment in my college life where I was like, oh, I actually have to know SOHCAHTOA crap. You do, but I am doing it backwards every time. Like, you might be used to using the angle. No, you might be used to using the sides to get the angle in math. We are tending to always have the angle and use it to get the sides, and we're always tending to get the legs, because what we're always doing is saying, like, as much as this looks like trigonometry, these are just numbers, right? Sine of 30 is 1/2. If my calculator is in degree mode, or if my brain is in the right place, sine of 30 is 1/2. So this is the number 1/2 times 8, meaning 4. This is like the number 4. And this one here is harder to do in your head, but it is, you know, the cosine of 30 is radical 3/2. That is like 1.765 or something like that. And it's radical 3/2. Oh, yeah, I mean, divided by 2. So it's like 0.866. Like cosine of 30 is like 0.866, I believe, times 8. So in other words, like 86% of 8, or like 86 hundredths of 8. And that's like 6.92, I believe. Yeah, around 6.92. I'm not saying you have to memorize, but what does that mean? It means what we're really saying here, and I haven't solved the problem yet. I haven't done the addition. I'm just working out the insight that Justin and Armand put in the chat, which is, it's the insight that Sarah first put. Like, yeah, we totally have to take advantage of right triangles, but the right triangle that we're always going to take advantage of is every single vector itself. Any vector that looks at all hard, any vector that doesn't just point north or east or south or west, any tilted vector, and there could be a million of them, is itself the hypotenuse of its own right triangle, whose legs are the x-axis and the y-axis. Really, this is what's going on in lab 3. So I'm saying what we just figured out is everything we need to do the addition. We're saying that really, when we went 8 at 30 degrees northeast, what we really did was we went like 6.92 approximately to the east, and then we went like 4 to the north, or maybe we did in the other order. But or if we had done that, that's equivalent. Going 30 degrees northeast is equivalent to going 4 north and going 6.92 east. Those are called the components. This is the y component of the 8 displacement, and this is the x component. And why that was all necessary is because we can now go back to this chart that we set up and say, oh, okay, now the second vector took a moment of trig or a moment of work, but having done the work, having zoomed in on that second vector, the second vector, it seems, brought us 6.92 to the right, like I'm positive, right? Notice for this whole system, I'm assuming there's positive and negative independently operating on each axis, but specifically on the x-axis, I'm thinking east is positive and west is negative. I'm not just thinking it, I put it in the original drawing, right? I mean, we have to be, it's here, whatever, in blue, but north is positive, south is negative, east is positive, west is negative. Whatever we decided, we're just being consistent with. So here, the second vector brought me 6.92 positively east along the x-axis, while it also brought me positive 4 up the y-axis, right? So what we now have is the first vector, how much it brought us x and y. The second vector, what it brought us x and y, and we're adding them up because that's what the problem is asking us, to add these two displacements to get our total accumulated displacement. So according to this, what I did was go a total of 6.92 approximately meters to the east, right? Again, picture lab 3, like, so the first vector didn't bring me at all east or west, it just brought me nowhere east. Like so you can picture like hovering above in a helicopter and just like shining light on just one axis or the other and just watching the individual shadows of this motion. I mean, not to be weird. And you'll notice that the first motion, if you're looking from a helicopter, it went along the y-axis, but it just didn't do anything on the x-axis. So it just like was as though it stayed on the x-axis, the same place. Then the second vector, while it was going north, it went to the east. How much? 6.92. And how much did it go to the north? Well, not all the way 8. It went 4 to the north. Right? Sorry. The second vector went 4 to the north. So the total to the north was 9. Like, each vector contributed some northward motion to this, and one of the vectors also contributed some east. So there was a total amount of 9 north motion and a total amount of 6.92 east motion. We're still not at an answer, right? We're just about there, and I'm going to pause for a second. We somehow then the people who've gotten this answer right put those together to get 11. Like somehow they put this 6 and it's 9 to get 11.4. How the heck can 9? Well, that's where the Pythagorean comes in, and where did they get the angle? I'm going to pause for a second while we're almost there, but you now have, what you now have is a big right triangle with one big X side, one big Y side, and you now can get, whoever you are, can get the hypotenuse through Pythagoras, and then you will have had 3 sides, so then you definitely can get the angle using SOHCAHTOA, which I'll do in a moment, but I'm going to look at the chat to catch up. I think there's a bunch of things, they may all be private. Hold on. Oh, and great question. Oh, okay, sorry. Yeah, so I'm not, okay, hold on a second. And once. Awesome. Okay, and hold on, just bear with me, everybody. But yes, and again, I have to say, the worst thing I can say about anything that I'm getting in the private chat, is that some of it is so good that it should have just gone in the public chat. And I do mean that, and it would therefore get points, and it gets points even if it's just then repeated in the public chat. But some of the private chat is being used exactly the way it should, like for like appointment stuff, which I totally appreciate. And then, so just everybody bear with me, but I definitely feel like this is a class more and more. And again, the more we can get it all public besides appointments is great, but yeah, great. Okay. So yeah, I'm seeing it. One sec, almost there. And in fact, one of these,
Professor,
yes.
I have a quick question. So
Okay.
with this method, is it fair to say that it's only really used when you have like two vectors, or can you use this for other, like say you have three different things or like four different?
That's a great, oh, sorry, go on.
Oh no, I'm done. I'm sorry.
Okay, no, that's a great question. I totally want to answer that public. Give me just one before I lose before my train of thought crashes at the station. Give me one. But no, that's a really important question. And there's also a really important question someone put in the private that I want to answer. So yes, hang on one second. I'm so sorry. I didn't think this could actually happen in 1 second. Okay. All right. And I do want to draw, first of all, I'm going to forget, but the question that what did we do? That I think Alyssa just asked, and now I'm lost. Wait, I'm totally lost where I am in the, but that's a great question about this method that I'm trying to teach everybody, or that we're seeing right now, or that we're inventing. This method is one of the powers of this method is it's for as many vectors as you want. And often we do have a lot of vectors to add. This method is not just for two. It's for three or four or as many as you want. It's literally, this is like literally how we add vectors. So it's like we're learning addition in space here. So it's like addition that you learn in third grade with numbers in that, yeah, once you know how to combine, it's for combining as big groups as you want. That's in fact the power of it. And in fact, it's really important that Alyssa asked that because like often if you just have two vectors that you're adding together, you often by chance might just see a right triangle. Like I might walk north and then walk due east. So you might automatically have a right triangle right there, which would have made Sarah's life a lot easier. And it can happen where the actual situation with just two vectors already is an automatic right triangle. But then that gets really confusing because then you have extra right triangles and it's possible to do things that work there that don't work in general. So what's powerful about this method of breaking each vector into its own right triangle is that it works for as many vectors as you want, but with one restriction, and this is also why I'm glad Alyssa asked it. I think it was Alyssa. With one restriction, which is that they have to be as many vectors as you want of the same kind. Like we can use this method to add 100 displacement vectors, and we like will, or 100 velocity vectors. But there's no method on Earth that allows you to add a velocity vector to a displacement vector. Like you literally can't do that like at all because it doesn't make any sense. But so as long as we obey that, then this, God, okay, oh, cool. Okay, cool. Other thing though, someone else asked me, and I'm babbling now because I've lost the screen. I've lost my Zoom screen. Oh, I'm sorry. Oh, there, okay. Someone else asked me something. Now that question that I think I just answered, yeah, that was Alyssa's question. And that was a public question, and I'm totally glad. And yeah, it's one of the reasons we have to learn this method. There's ways to get through vector problems. There's a lot of vector problems that can be constructed where people can just sort of grunt their way through them from like remembering crazy things like law of cosines or something like that, or law of sines. That can work in crazy circumstances. So you can like beat up these problems with some really brute force math sometimes, but very rare times and not like exam times. So people can get confused if they just get vector problems right with their own ways, but then the rubber will hit the road if they try to add 3 vectors or something. So totally what I'm trying to teach everybody in terms of what Alyssa was asking is, yes, this is meant to be the all-purpose general method that is just an extension of Galileo. But now another question came up in the private chat. Oh, wait, and I'm sorry, I really should finish this problem too. I should finish solving this. Oh my God, yeah, I will. But the other question in private chat is, at steps along the way or in the final answer, do I prefer things like 3 radical 2, or would I prefer an approximate like 0.866? I may have addressed this before. I want to maybe address it in greater length another time again, but in physics, I will accept either in an exam, when in doubt. If you think an answer is right and you can say it in a way that makes sense to you, say it in the way that makes sense to you. And if it is right in an exam, you'll get full credit probably either way. But my preference always, my advice in physics is every step along the way and for final answers, always choose approximate over exact. Always choose numbers that look like actual numbers that you could imagine being on a ruler or like some kind of instrument, rather than numbers that are exact and lovely in a math class. But like radical 3/2, we would never see on a ruler. And I can't in my head add radical 3/2 to like radical 2/3. The way I could just add 0.866 to 0.412, something like that's a guess. But I can do those in my head if they're said as numbers, but you can't if they're said exact. So but it's still a fair question. Math is for perfect exact, but not measured. Physics is for measured, but not exact. But now I'm rushing because I absolutely should finish this. Oh God, we have like one. Let me just, how did I get the final answer? Hopefully this will be clear. Is I took my 2 last entries from the chart. I mean, this may be obvious to some people, but I took the last 2 entries and I totally paid attention to pluses and minuses. And here's the key thing to everybody. I always draw horizontal first, and then I do tip to tail from horizontal to vertical. In other words, and there's a reason for that, otherwise you get messed up, trust me. So I take the 6.92 from the bottom of my chart that is positive. So I draw it to the east. From the tip of that, I go up to the north. I go up the positive 9 that the chart asked me to go. So that should be a lot longer. So this is like not beautifully to scale, but so, that should be like, so I go 6.92 across and 9 up. So my final answer for the whole thing is the Pythagorean theorem of 6.92, the square root of 6.92 squared plus 9 squared, which is approximately 11.4 meters. And that's how we would want the answer. And it's like 3 significant digits. In other words, it's greater than 9, and it's greater than 6.92, and it's greater than 8, and it's greater than 5, but it ain't 13, right? If you walk 5 and then you walk, and I'm watching the time and I'm yelling, but the key lesson here is if in two-dimensional space, in vectors, 8 plus 5 is not 13, right? We walked 5 and then we walked 8, but we didn't travel 13. We traveled like 11.4 meters because angles were involved, because we didn't do the 8 in the same direction as we did the 5. So we get like 11.4 from the Pythagorean theorem. And here's the last thing, and then we'll go. This angle is what we want. That's the angle we want. How much north of east did we go? Well, the most straightforward way to get it would be to know that tangent of angle, you could do anything, but since I have the leg staring me in the face, I always do tangent. Tangent is opposite over adjacent, i.e. in this case, 9 over 6.92. So the tangent of that angle, arguably I skipped a step. I'm saying the tangent of that angle is equal to the opposite over the adjacent. Therefore, the angle itself is the arctangent or the inverse tangent of that fraction. And that is a number that is greater than 45. You get that on your calculator for sure. And I got it on my calculator. I knew that if it was less than 45, I had made a mistake. But so I got 52.4 degrees northeast, like literally that is north of east because of the way all the arrows are drawn. That's the answer. I think you guys all rocked it. I think there were other questions. I think I've answered. Oh, wait, let me look at the chat. I think I've answered all. Yes, sorry. No, thank you for the heads up. All right, so now I think I just like went one way. Sorry, I went 2 minutes over. I'm going to shut. Goodbye. I'm going to end the meeting so the other people don't come into the. But keep going the way you guys are rocking. Seriously. Okay. Bye.